हो सर दिसतंय.
हां सर फर्स्ट स्लाइड वर. हां
Yes,
ओके फर्स्ट स्लाइड वर या सर.
हां हां एक मिनिट.
आणि फुल स्क्रीन केला की होईल. प्रेझेंटेशन मोड. फर्स्ट स्लाइड इन प्रेझेंटेशन मोड.
एक मिनिट.
हो सर.
हो आपलं सर.
Can you see?
Yes sir.
दिसतंय?
Yes sir.
प्रेझेंटेशन
दिसतंय. प्रेझेंटेशन मोड ऑन करा सर.
मोडवरतीच केलं ना, नाही केलं. अच्छा ओके. So am I audible?
Yes sir.
Yes sir, you are audible. First of all, let's start my introduction. Good evening everyone. Priyanka Birla from Cement Pune this side. I'm so pleased to be with you all this evening and to have the chance to introduce our guest speaker. On behalf of Cement Pune and the project team, I welcome all of you here for today's lecture. Today's session is arranged as a joint activity under Azadi Ka Amrit Mahotsav, Swachhata Pakhwada 2022 and the project entitled as Creation of R&D Culture in Electronics Material among SC, ST and women students from rural areas in Maharashtra. Without taking much time, I would like to introduce our today's guest speaker. Today we have an eminent speaker, Professor Dr. Prashant Alegaonkar sir. Currently, he is holding a position of head of the department at Department of Physics at the School of Basics and Applied Sciences, Central University of Punjab, Batinda. Dr. Alegaonkar sir completed his PhD and MSc from Savitribai Phule Pune University, Pune. His area of research experience in the field of chemical vapor deposition best, large area, gram scale, graphene synthesis, and their integration for useful application in defense sector. He has completed many major minor sponsor projects and now there are few ongoing projects. His scientific contribution has been recognized and published in highly reputed international journals. He has published more than 155 research articles, authored one book as well as 7+ book chapters, and he also have one German patent on his name. He is also a recipient of highly prestigious awards and honors. He is also a member of many scientific bodies in India as well as abroad. I welcome here Dr. Alegaonkar sir to deliver his talk. Welcome sir.
Thank you madam. Thank you so much, and thank you Amol for arranging this wonderful event. First of all, which language, Marathi or English or semi-Marathi, semi-English?
Yes sir.
Semi-English, semi-Marathi sir. That would be better.
Yes sir.
Because all the students are from rural background.
Yes.
So it will be better if we speak in English. If you can speak in Marathi first.
Yes. तर सर्वप्रथम मी तुम्हा दोघांचे आभार मानतो. अमोल तुझे पण, मॅडम तुमचे पण आभार मानतो मी की मला तुम्हाला तुमच्यावर इंटरॅक्ट करायला संधी दिली. ऍक्च्युली मी बघत होतो वाट की आपण भेटूया आणि एकत्र काहीतरी काम करूया आणि आपण सर्वांनीच हा आता गोष्ट केली पाहिजे की आपण कॉन्फिडेंटली आणि ज्याला आपण म्हणतो की डिटर्मिनिस्टिकली पुढे आलं पाहिजे आणि काम केलं पाहिजे. आणि मला असं वाटतं आपल्या महाराष्ट्राच्या लोकांमध्ये खूप पोटेन्शियल आहे आणि आपल्या महाराष्ट्राच्या लोकांचं रेप्युटेशन ही बाहेर खूप चांगलं आहे. जसं मी
Excuse me sir.
Yes.
Please, we are non-Marathi students, so can you please talk in English?
Acha, so there is a mix. So there are some non-Marathi also. So what should I do? So
Maybe you can talk in Hindi.
Okay. So okay. So Marathi, English. Let us do it like this, sir. We will go it like this. I will talk in English and then some part of it will be in Hindi. Okay. And then there'll be guys from rural areas of this thing. So I will have some little bit of Marathi also. So what I was telling to all that, yes, you got it. Huh? Thank you so much. So या तांबे तुझे 4 कॉल आले रे, पण माझा फोन फार्मास्युटिकल लॅब मध्ये होता, फार्मास्युटिकल डिपार्टमेंटला होता. आता पोरा हा घेऊन आला. सो फर्स्ट ऑफ ऑल आय एम थँकफुल टू ऑल, अँड आय मस्ट से दॅट रुरल स्टुडंट, जे रुरल स्टुडंट आहेत आपल्या महाराष्ट्राचे, ते शुड कम अप अँड वर्क कॉन्फिडेंटली. ओके, त्यांनी कॉन्फिडेंटली काम केलं पाहिजे, आणि this will be a wonderful thing for them. There are a lot of things which are emerging. Okay, and I must say that recently, as I was
हॅलो. हॅलो. हॅलो सर. हॅलो. हॅलो सर.
आवाज येईना झाला. हाय, हॅलो.
हा सर बोला ना. ओके. हो हो, चालेल चालेल. ओके 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 सर. म्हणजे सांगतो मुलांना मी तसं, काय प्रॉब्लेम नाही. चालेल, सांग.
आवाज नाही येते ना?
नेटचा प्रॉब्लेम झाला. नेटचा प्रॉब्लेम झालाय जरा. इथे चालू आहे, नेटचा इश्यू झालाय थोडा. हा सर बोल ना. हो चालेल, हो चालेल sir. हो हो चालेल. नाही ते काय एक मॅडम ते सरांच्या मिस्टर नेमक्या ते हिंदीच्या आहेत बाकी मराठीत बोललं तरी इंग्लिश मध्ये बोललं तरी मराठीत बोलायला पाहिजे. प्रॉब्लेम नाही.
Am I audible?
Correct sir.
Yes.
You can share screen.
Shall okay. Yeah, I'm sharing screen now. I'm just putting it. Okay.
Just make PowerPoint.
That's fantastic. Can you see the screen now?
Yes sir, yes sir. Just make a screen. Presentation mode. All is okay.
Just a minute. Can you see now?
Yes sir, yes sir, yes sir.
So okay. So मी तुम्हाला ही बातमी ही दाखवली ही रिसेंट आहे आठवड्याभरापूर्वीची. त्याच्यामध्ये आपलं जे MIDC जी उद्योजक संघटना आहे चाकण MIDC त्यांचे जे अध्यक्ष आहेत जे महासंचालक आहे मराठा चेंबर ऑफ कॉमर्सचे. So they have been most probably we will have a we will be having ample of semiconductor. So it is not semiconductor material, actually it's a IC. आणि जर का तुम्ही आता करंट बघाल हार्डवेअर मध्ये, so there is a waiting time of 9 to 10 months for various type of IC. If you go to hardware industry, especially assembly industry and this thing, so there is a hardware waiting time of this ICs more than 9 to 10 months. So it is like, but we are going to talk. So today's content of my talk, I hope I am audible to all.
Yes sir, yes sir.
The content of my talk, we will just see the background and what is the government initiative and what are the challenges. Okay, so we are going to talk about foundry to fabrication, and then we'll see some basic science of silicon. So it's like a top down approach kind of thing. So initially we'll see what is there in the market, and then we'll see some part of some part of basic science which most of you may be knowing. So now I always tell this की तुम्ही बघा 24 तासामध्ये तुम्ही कोणते कोणते इलेक्ट्रॉनिक डिव्हाइसेस यूज केले. आप देखो 24 घंटे में पिछले क्या क्या इलेक्ट्रॉनिक डिवाइसेस आपने यूज किए. देयर आर लॉट ऑफ एवरीथिंग यूज is digitalized and it consists of some electronic devices which has which has at least a semiconductor chip in it. So it means that when we talk about this semiconductor device or electronic devices, it has a heart, and then this heart is made up of a semiconductor chip. We are going to talk about that because In India, we don't fabricate it, but we are now planning. So if you talk, जर आपण सेमीकंडक्टर चिपचा विचार केला तर त्याच्यामधले जे ट्रान्झिस्टरची जी संख्या आहे, number of transistor which act as an on and off 0 and 1 bit by device, okay, it is more than the Great Pyramid, the number of stones which are there in Great Pyramid of Giza. So there are billions and billions of transistors which are there, and then this their miniaturization and their number is increasing. We are going to see that also. So we are going to talk about that. तुम्हाला मी ही गोष्ट याची सांगतोय आजपासून 2 वर्षापूर्वी, 1.5-2 वर्षापूर्वी, 1.5-2 साल पहले जब फर्स्ट लॉकडाउन लगा था, इट वाज अ वेरी सीवियर लॉकडाउन. और ऐसा लॉकडाउन होता की सगळं शटडाउन होतं. आणि इवन एज्युकेशन हॅज गॉन ऑन ऑनलाईन मोड and everyone was going for mobile and laptop based education. ज्या लोकांकडे लॅपटॉप आणि मोबाईल नव्हता त्या लोकांनी आठवायचं, उन्होंने याद करना है कि अगर आपको अच्छा लैपटॉप लेना है, if you want to have a good laptop, okay, then there was a waiting time. याद आ रहा है आपको? That was the situation. Why? Because why there was a waiting time? Because during that time more than 200 industry globally were affected, and these industries were digital industries, automobile industries, communication, healthcare, instrumentation, the software related industry. All of them, they were affected. Why? Because of the semiconductor part. In Taiwan and China and Korea, where they fabricate and send this hard to all these things. The rest of the people, they make assembly, including India, but they don't prepare hard, means semiconductor chip. That was completely shut down. Wuhan virus, because of this COVID thing, everything was shut down. Still, in today's time, आज के डेट में भी जो हार्डकोर हार्डवेयर इंडस्ट्रीज है उसमें वाइटल आईसीज का वेटिंग टाइम है, 6 month है, 8 month है. Still that picture is there because of this all backlog and this excess demand, and only few people are there, only few countries are there. We are going to talk about that. But looking at those anxieties and those type of things, government has taken the initiative that this production link incentives, PLI based investment, government will do. It is worth of 1.7 lakh crore in next 6 years. And then among this thing, 50%, so it is the MSME based thing. There will be government will be establishing various MSMEs under this, and one such MSME will be going to come to Chakan MIDC, Moshi मध्ये येणार आहे. And in all there will be 3 MSMEs which will fabricate, which will have a foundry processing of this thing. When will come into Chakan, one is going to come to Gandhinagar, Gujarat, and third one is going to come to Greater Noida, Uttar Pradesh. So these 3 where we are going to fabricate this thing, we will have this initial installation for this thing, and government is going to put 50%. Okay, there are 2 types of semiconductor thing. One is hardcore semiconductor industry, another is a vital component, that is display industry. And you know who is the world leader in display, right? Samsung. Okay, so they have excellent fab labs, okay, in Korea, South Korea. And then with this initiative, government will have R&D center, skill development center, की ज्याच्यातून आपल्या ग्रामीण जे आपले विद्यार्थी आहेत त्यांना त्याचा फायदा होणार आहे, त्यांना त्याचं R&D करण्याची संधी उपलब्ध होणार आहे. फक्त एवढंच आहे की तुम्हाला ती माहिती असलं पाहिजे. So that was a cause and effect during the lockdown which provoke government to think about have his own semiconductor industry built indigenously in India with the help of other countries. So if you see, there are a lot of things came. More than 75,000 crore we will put as an initial investment, okay? And a lot of promising things came from the So you see, Piyush Goyal has said that the government will support establishing semiconductor industry. Okay, and then there will be a adequate infrastructure. Okay, there will be bigger fab factories will be there. There will be semiconductor two. There will be two display industries, two semiconductor industries that are going to go, and then there will be a development of semiconductor ecosystem. Okay, but then the question comes that are we ready for that? Are we ready for that? So our chip production is still a long way to go. Because why? Because we need manpower being developed to cater this industry. We need skillful people. We need certain things which are required. Okay, to set up such type of industries. So now let us see. Let me go ahead. Am I audible to all?
Yes, sir.
Yes, sir.
Okay, this PPT is not moving. Just a minute. So the greater challenge in so the question सवाल ये है कि are we ready? हम लोग ready है क्या ये करने के लिए? क्यों? क्योंकि only few countries they have mastered this making of this fabrication of this ICs and chips, and rest dependent on its import. And the leading agents of the leading countries are like TSMC, Taiwan Semiconductor Manufacturing Company, and South Korean Samsung Manufacturing, which has a share of 70% distribution to the world's semiconductor. So they have, you see, they have a very big share. Okay, तुमच्याकडे खूप मोठा शेअर आहे की जे तयार करतात. 70% सेमीकंडक्टर जे आयसी फॅब्रिकेशन आहे ते या दोन कंट्रीज मध्ये होतं, तैवान मध्ये आणि साऊथ कोरियामध्ये. आणि इनफॅक्ट आपल्याला जेव्हा प्रॉब्लेम आला, तुटवडा आला, शॉर्टेज आला, फोन मिळेना आणि हे मिळेना, लॅपटॉप मिळेना. इफ यू रिमेंबर 2020 March, August, September, when you thought when it has been come ki you have to work from home, then we started searching on laptops and things like that. Just a minute. Hello. Yes. Yes. Thank you. So only
Yes,
few
sir.
have mastered this technique, and rest is dependent on its import. Okay, and basically role of the industry comes from the specialist. So we need to develop specialists for that, and then this is a welcome move. I mean, everyone has a right to to nurture as a specialist, so to become skillful. This is a welcome, but then its implementation is a bit challenging. And so if you ask for the self-sufficiency or make in India as far as in the semiconductor industry is concerned, then it is still complex. Why it is complex? Because it need both things, capital as well as it is technologically intense process. Okay, so we are going to see what type of challenge. So see, when you talk about the silicon firms, there are two types of firms involved. One is foundry based, other is the fabrication based. So there are two main stages of production. One is the designing of the silicon, other is the manufacturing of the silicon. And all manufacturing based thing is called as foundries, okay, where you have to actually make silicon. You have to actually make the silicon smelt. Okay, actually we have to make a silicon wafer. And then next part comes the designing. And if country is capable to do both, then this both thing integrated together is called integrated device manufacturing. जर का देशामध्ये क्षमता असेल दोन्ही उत्पादन करणे, म्हणजे एकामध्ये कसं सेमीकंडक्टर हे तुमची हे बनवायची सिलिकॉन वेफर बनवायचा, दुसऱ्या ह्याच्यामध्ये त्याच्यावरती डिझाईन करायचं. काय डिझाईन करायचं तर सर्किट डिझाईन करायचं त्याच्यामध्ये. आणि जर का देशामध्ये क्षमता असेल दोन्ही बनवण्याची, देन इट इज कॉल्ड एज अ integrated device manufacturer. And then currently we are in a process to set up this IDMs. Okay. So how to get silicon? Silicon is a basic element which comes from the silicate, which comes from this जी वाळू आपल्याला आहे त्या वाळूमध्ये फुल ऑफ सिलिकेट आहे. आणि जो सिलिकॉन मॅन्युफॅक्चरिंग आहे, the silicon means fabrication of silicon wafers. So if you see in this image, you see this, these are all silicon wafers on which we have to design our circuit, which we have to design. So it is like a 4-inch silicon wafer, 6-inch silicon wafer, 8-inch silicon wafer, 12-inch silicon wafer, 14-inch silicon wafer. So this is the thing, basis on which we have to have a silicon, we have to have a fabrication of the devices. And this thing, या जे संपूर्ण दिसतो हा दांडा, त्याला इंगोट म्हणतात. इंगोट ऑफ semiconductor, ingot of silicon. So this is the thing which we have to exactly fabricate. Now what it will do with this, we will have this type of beautiful thing, okay, to be made. LEDs, ICs, transistors, capacitors and things like that. So that's why silicon. But how to make it? हे सगळं बनतं कसं? सिलिकॉन मॅन्युफॅक्चरिंग हे खूप मोठी जटिल प्रोसेस आहे. याच्यामध्ये कसं असतं की इट्स अ फाउंड्री प्रोसेसिंग इन विच arc furnacing is done. So what it consists of? It consists of a huge graphite electrode, very big electrode, maybe the size of a two-story, three-story building. Okay. And then this consists of a arcing at the bottom. You can see over here. आणि याच्यामध्ये वर्ण वाळू टाकली जाते. काय टाकली जाते? वाळू टाकली जाते. आता ही नुसती वाळू टाकून उपयोग नाहीये, कारण की वाळूपासून ऑक्सिजन सेपरेट करणं सिलिकॉनपासून जरासं अवघड आहे. तर त्याला सेपरेट करावं लागेल. काय करावं लागेल? त्याला अशा गोष्टीचं विघटन अशा पद्धतीनं करावं लागेल, असं त्याला डिसोसिएट करावं लागेल की तो इझिली बाहेर निघून जाईल, इझिली बाहेर पडेल. तर मग हे कसं करायचं? हाऊ टू डू इट? सो वाळू टाका, त्याच्यावर लाकूड टाका आणि त्याला आर्क द्या, जळवा, त्याला जळवा. सो वन्स यू पुट इलेक्ट्रिक आर्क and heat it up to 2000 degrees Celsius, then what is going to happen? That it will have, there will be a reaction, very simple reaction. This will get dissociated, याचं विघटन होईल आणि कार्बन हे कुठनं आलं? लाकडापासून आलं. त्या कार्बन बरोबर त्याचं विघटन होऊन सिलिकॉन बाहेर पडेल आणि कार्बन मोनॉक्साईड तयार होईल. पण ही जी गोष्ट मी तुम्हाला दाखवली आहे ही अतिशय ढोबळ मानाने दाखवली, तुम्हाला समजायचं असं. ऍक्च्युअल प्रोसेस खूप multi-step hai. There are multi-steps involved in that, because silicon will not directly transform into silicon and carbon monoxide. Silicon will have a native oxygen to be there, so it will be always silicon oxide, and then this silicon oxide we have to further process to get a silicon, pure silicon. Okay. So but then by and large ठोकळ मानाने समजा बघायला गेलं तर if you lower the sand including wood, okay, and if you gradually increase temperature, you will have this silicon. And how this silicon will look like, still you can see here, it's not pure silicon. This is silicon, but this is silicon dioxide. This is how you will get a ingot kind of thing, or this is how you will get a substance which will look like this, which will have both things, silicon as well as silicon dioxide. Then you have to separate it out. Okay, again you have to process it so that you will get a silicon. So this is his घडतं सिलिकॉन मध्ये. हे आपल्याला करायचं, हे बनवणं हे आपलं उद्दिष्ट आहे. मग आता हे एकदा मिळालं तुम्हाला सिलिकॉन, की मग पुढं काय? Once we get this silicon, how to make a wafer, because wafer is very, very important. So what to do? That you take this silicon, chunk of this silicon, and then you put it into a heating furnace. This is a heating furnace, फर्नेस आहे, हीटर आहे, त्याच्यामध्ये या भट्टीत टाकायचं. या भट्टीमध्ये जे आहे ग्राफाईट आहे. ओके, आणि या ग्राफाईट वरती हे सगळे तुकडे टाकायचे असे. दिस इज अ इन्फ्रारेड हीट शील्ड and this process is called Zusalski growth process. This was developed by a Russian scientist, metallurgist, whose name is Zusalski. Okay, and he was a metallurgical engineer. So ही जी प्रोसेस आहे यातनं सिलिकॉनचं विघटन होऊन सिलिकॉन डायऑक्साईड आणि कार्बन, या प्रोसेसला मेटलर्जिकल प्रोसेस म्हणतात. काय प्रोसेस म्हणतात? मेटलर्जिकल प्रोसेस म्हणतात. दिस इज कॉल्ड मेटलर्जी. सो व्हॉट वी हॅव टू डू, वी हॅव टू पुट दिस इनटू हीटर and then heat it. So as you start heating this thing, there will be a melting of silicon. Silicon will start melting. This is around 1900 to 2000 degrees Celsius. And then slowly what you have to do, then what you do is that you bring the seed crystal into the silicon melt. This is called smelt. Silicon melt is called smelt. So you lower this thing into this seed crystal, okay, so that it will start nucleating the thing. To start nucleating the crystal, because you know that आपण जसं सीड त्याच्यामध्ये टाकतो तर ते त्याच्या भोवती क्रिस्टल तयार करायला सुरुवात करतात. आणि मग जसं तर क्रिस्टल तयार होईल त्याला असं वर खेचायचं. काच कसं बनवतात? काचेचं बघितलं की नाही? काचेपासनं बाउल बनवतात किंवा काचेपासनं फुलदाणी बनवतात. एक्झॅक्टली त्याच पद्धतीने करायचं, कारण की हे काचेसारखंच द्रव्य आहे. हे काय? काचेसारखंच द्रव्य. मग त्याला ओढायचं. ह्याला म्हणतात इंगोट. काय म्हणतात? इंगोट. याच्यामध्ये कसं असतं की याच्यामध्ये जे खालचा जो फर्नेस असतो तो एका दिशेने फिरतो आणि वरचा जो फर्नेस असतो एका, आणि त्याला असं ओढायचं काचेसारखं. So it will start coming the, and then you can adjust diameter of this ingot. So once you start getting it, okay, once you start getting this, okay, then what is going to happen, that this will come like this. You pull the seed, and once this is done, then you will see that this is what you will have. This is what you will have, a complete wafer. हा तोच वेफर आहे जे तुम्हाला मी मागे दाखवला इथे. कुठे? हा तोच वेफर आहे. इथनं ओढलाय बघा. दिस इज कॉल्ड इनगोट. दिस इज कॉल्ड, हा इथनं ओढलाय असा. सो हा आता बनला, असा आपण गेलो याच्यात बनला आहे की मग काय करायचं, त्याला थंड करायचं. देन यू हॅव टू cool down the temperature. You lower the temperature of the furnace, and next is the grinding. Next is the, what is the next process? Next is the grinding and slicing of it. So how to do that? This is your ingot, and then you have to cut it. You have to do some ground what to do of the desired diameter. 4-inch wafer, 6-inch wafer, 8-inch wafer, 12-inch wafer, 14, depending on gallium arsenide wafer मोठे असतात. Okay, they are like 14-inch, 18-inch wafer. But generally silicon wafer, 4-inch wafer, 6-inch wafer, 18-inch wafer. So then you ground it. Okay, त्याला कट करायचं असतं, तासायचं. You ground it in such a fashion that you will get this ingot to be clean, and then add a orientation flat. Those who have used, ज्यांनी सिलिकॉन वेफर वापरला त्यांनी बघितलं असेल त्या चकतीला असा एक कट असतो. चकतीला असा एक इथे कट असतो, त्याला म्हणतात ओरिएंटेशन फ्लॅट. व्हॉट इट इज कॉल्ड? ओरिएंटेशन. वाय विच इज ओरिएंटेशन फ्लॅट? कारण इथून कट मारत असतो पुढे, याला कापायचं असतं. म्हणजे हा अजूनही ब्रेड सारखा अखंड आहे. लादी पाव असतो ना त्यासारखा अखंड आहे. नाउ वी हॅव टू कट इट इनटू स्लाइस. सो दॅट्स वाय वी हॅव टू मेक ए ओरिएंटेशन फ्लॅट. So once we got this thing, okay, once we have added orientation flat, then we have to go for this what it is called is a wire cutting process. What it is called? It is called wire cutting. What it consists of? It consists of 3 roller. One is the feed roller, other is the rotator, and third is the apron roller. आणि ह्या 3 रोलरच्या मध्ये हा इंगोट जो असतो ह्याला बसवला जातो. आणि हे खाली कट दिसतोय का? हा, यू कॅन सी दिस कट. ओके, देन व्हॉट इट इज गोइंग टू हॅपन, दॅट वन्स इट इज फिक्स ओव्हर हिअर, देन दिस थिंग विल स्टार्ट पुटिंग अ प्रेशर. हा जो फीड रील आहे, हा रील त्याच्यावरनं मूव्ह व्हायला लागेल आणि हे दाब द्यायला लागतील त्याला. आणि जसं हे दाब देतील त्याला दिसते खालनं कट आला. अँड यू विल सी देर आर वेफर्स विच आर कमिंग आउट. आणि ह्या कसल्या वायर असतात? हे वायर जे असतात या वायर स्टेनलेस स्टीलचे असतात पण त्याच्यामध्ये डायमंड असतो. पतंगाचा मांजा कसा असतो, त्याला काचेचा हे असतं, त्याच्यावरती काचेचे तुकडे असतात, छोटे छोटे बारीक 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 काचभोगटीचे. तसे इन सिमिलर फॅशन दिस semiconductor this steel thread is having a diamond, okay, diamond powder, so that it is very easy to cut, because it is very easy to cut silicon wafer using diamond. Very easy to cut silicon wafer using diamond. So this is how you will get a silicon wafer flow. So you see 1 wafer, 2, 3, 4. This is the cut. Yes, this is the cut. Okay. Once you get this, then you have to do lapping and etching. That is the next process, because if you see, there are a lot of surface defects. Physical cut केल्यामुळे, what is going to happen? There are so many surface scratches are there. Now we have to make a polish. We have to make it. So imagine that this is like a glass. Okay, this is like a glass cutting, similar to what do we mean glass cutting. So this is called lapping and etching. So we have to have a furnace in which you have to put this sample. They will start rotating, okay, and then you start polishing. Okay? And this process is called lapping and etching. त्याच्यामध्ये दोन गोष्टी असतात, एक तर लॅपिंग इनिशियल पॉलिशिंग, आणि त्याच्यानंतर इट इज फॉलोड बाय द क्लिनिंग ऑफ द एचिंग, and this is called wafer dicing. Okay, wafer dicing and etching. So काय करायचं की हे वेफर तयार झाले की still there are some surface defect, surface roughness that has to be smoothed out, and then for that what you have to do, you have to put it into the solution. So this is a chemical process where you have to put this silicon this thing into this HFHNO3. Okay, on this thing you have to put, and once you put that, okay, then they will remove the damaged wafer of the surface. ते काय करते, त्याच्यामध्ये जो इसमें जो डैमेज हुआ है, surface damage है, वो निकाल देना. This is a purely a chemical approach, and once that is done, then next process is polishing and cleaning. Still we have to mechanically clean it, and then how to do it? There is a mechanical and chemical slurry. Okay, and then this polishing is done on both the sides. या दोन्ही साइडला हे पॉलिशिंग केलं जातं. Okay, and then this is called polishing and cleaning. So why to do this? Because it should be then as smooth as atomic smoothness. तुम्हाला जो वेफर मिळतो, it is mechanically and chemically smooth, so that there will be atomic smoothness to that wafer. You will have like a glass. Okay, you are looking at a glass kind of thing, black glass kind of thing. Okay, so this is done in polishing and cleaning. Now if you look at this setup, ऐसा आपल्याला जर का सेटअप ऐसा बनाना है, तो requirement for setting up such a thing need huge investment. Why? Because for all these things you need gallons of water, uninterrupted electric supply, high operation cost. Okay, and then there is a need for frequent technology replacement. There is a need of frequent. Why? Because every time, if those who remember their first USB pen drive, it was just for some few MB, 500 MB or so, or maybe 250 MB or so. But now at the same cost and at the same size, now you can get a pen drive of 1 terabyte. Okay, we don't need any external power supply and all this thing, and quickly data can be transferred and things like that. Okay, so there is a frequent replacement in the technology, so that you have to incorporate. You cannot have a key, okay, I will make it like this only. Why? Because there is a technological change. So once technology is changed, it means that your device operation is going to change. Device operation is going to change. You have to change your device engineering. When device engineering has to change, it means that you have to have a new things to be put into, including change in silicon itself, that we are going to talk at the end. So requirement of setting up for such a industry has a great challenge in terms of investment, money, okay, water, electric, and continuous upgradation of the technology. Now, second question comes here, what is fab? What is fabrication? So this is what I have showed you, the foundry process. Foundry process तुम्हाला दाखवलं. फॅब इज अ फॅब्रिकेशन लॅब. मी तुम्हाला ही इथली कोरियातली लॅब दाखवली. ही देगुला आहे सॅमसंग इलेक्ट्रॉनिक्सची. सर्वात मोठी जगातली फॅब्रिकेशन लॅब आहे की जिथे सिलिकॉन मॅन्युफॅक्चरिंग पण चालतं आणि इंटिग्रेशन पण चालतं. आणि सो सेमीकंडक्टर फॅब्रिकेशन इट्स अ मॅन्युफॅक्चरिंग प्लांट in which raw silicon wafer are turned into integrated circuit. So याच्यावरती मेहंदी काढली जाते सिलिकॉन वरती. मेहंदी काढली जाते म्हणजे इंटिग्रेटेड सर्किट त्यापासून बनवलं जातं. आणि काय लागतं त्याला फॅबला फीचर्स? That it need a clean room. It need a clean room where the environment is controlled by eliminating dust, vibration. The temperature is maintained, humidity is controlled. So that is a feature of a fab lab. That is another expensive tool which we have to put. Now, if you look at semiconductor industry, it has followed the Moore's law. It has followed the Moore's law. What is mean by Moore's law? If you see on this thing, it's a x-axis on which I have given year. So first integrated device was fabricated in 1970s. Okay, with some 1000 to 2000 integrated transistors. Okay, and then if you see, that was the era of 1970 where your first computer came, that is 4004 processor. Okay, that was the first. And now if you see here, it is AMD thing. Okay, which is a Italian company which is producing, and you see how many number of transistors have been integrated. They are like 50 billion transistors, and of course this data is still 2 years old data, so there is still upgradation. So it follows Moore's law, where the number of transistors are non-linearly increasing, okay, with respect to the year. And then if you look at European Commissions, then they have this public-private semiconductor alliance to enhance the global change. So they are also putting effort because there is a lot of market in South Asia now. We will be the greatest consumer of all these things. And then they are going to increase it by 20% by 2030. South Korea has already put $450 billion of investment through Samsung Electronics. And India is also now going to have its own IMSC, that is in India Semiconductor Manufacturing Company. So what is a chip? What it is considered? तुम्ही chip बघितली आहे का कधी? Yes, तुम्ही chip बघितली आहे. Visa card वरती असते बघा इथे अशी. This is called microchip. What it consists of? It consists of some security key, some so this micro. So Visa card मध्ये काय काय असतं? It is having some kind of security key, some personal serial code, some plastic emblem, hallmark असतो, hologram असतो. This is what is a Visa card. And then याच्यामध्ये एक microchip असते. And then this chip, which is called microchip, is a very complex device, or is a very complex tiny module which store the computer memory and provide logic circuit to the microprocessor. जगामध्ये कोण चांगले चिप बनवणार आहे, कोण अच्छे बनवते? इंटेल, ऍपल, मोटोरोला, IBM. Okay, they make chip for computers and workstation. Okay, so these are some of the chips. Photograph of chips I have shown for you how it looks like. Now, so how to make a chip? Chip कशी बनवली जाते? So chip making मध्ये chip making involve lithographic technique. What it consists of? Consists of lithographic technique. Am I audible to all?
Yes.
So chip making process consists of a lithographic technique. So what is meant by lithography? Lithography word, this word has a word ahead, is come from the Greek thing. Litho means stone, graphy means writing. So शिलालेख ज्याला आपण म्हणतो, that is nothing but the lithography. शिलालेख is nothing but it's a Greek from Greek this word has been taken. So similarly, we have to write transistors and devices on silicon. That's why it is called like a silicon lithography. So there are two types of writing we can do. You can do it by electron beam, or we can do it using using light. So it is called photolithography, electron beam lithography. So याच्यात काय करतात, त्याच्यात असतं की सिलिकॉन वेफर, you have to take silicon wafer, then you have to put a this thing photoresist. त्याच्यावरती मटेरियल टाकायचं आणि त्याला फिरवायचं, so that this photoresist will be spread uniformly onto the silicon. And then what you have to do, once you put this photoresist, then you have to put a mask onto it, so that this mask will create a shadow on the light. Mask will create a shadow on the light. Once you have this shadow, you put a light, so that what is going to happen, wherever there is a shadow, this photoresist will remain there. The photoresist light पडला त्याच्यावरती, इथे इथे जिथे जिथे खाली जिथे जिथे तो झाकला जाईल पोर्शन, the ones which will be shadow, तिथे फोटोरेसिस्ट राहील, बाकीच्या ठिकाणचा फोटोरेसिस्ट उडून जाईल. आणि मग काय होईल, ऍज अ रिझल्ट you will have this type of pattern. You will have this type of, so you take it, you spread it, you put a mask, you illuminate it with the UV light. And once you put it, the portion which is not exposed to light, okay, will remain as it is, and the rest of the thing will be dissociated. Now there are two types of things. One is called positive PR, other is called negative PR. ज्या ठिकाणी लाईट पडेल तो राहील, आणि काही वेळा ज्या ठिकाणी नाही राहणार तो राहील. दोन्ही टाईपचे पीआर आहेत, निगेटिव्ह फोटोरेसिस्ट आणि पॉझिटिव्ह फोटोरेसिस्ट. इथे मी एका टाईपचं दाखवलंय तुम्हाला की ज्याच्यावरती पडणार नाही, ज्याच्यावरती पडेल ते राहून जाईल. Once you have this thing, then you have to process it further. What you have to do, you have to go for the development kind of thing. So you immerse it into appropriate material, and then what you do, you cast, you make this pattern, you make this pattern prominent. And then what you have to do, you have to do etching of this pattern, to do etching, so that once you etch it, you remove the masking, and then you will have your lift off. Using lift off and metal layer deposition, you will have your primary device on this, deposited onto this thing. And then what you do, the next process is you lift off this also, so that you will have a written devices over here. So this process is quite complicated, and depends on what you want to write, what type of thing you want to put, what type of circuitry you want to put. Okay, and then once you have this thing, this is how your basic unit of this IC will look like. So there are many types of things. People use UV light. Okay, people use UV light and mask to have this ultraviolet lithography. This is called extreme EUV lithography. And then you can see this is how the wafer will look like, okay, after writing this thing. So, and this is the thing which is involved. You can see over here, okay, this is a polysilicon, and then this is a gate which is developed over here. This is a trench for isolation. This is a, and then from here the silicon beam is fallen, so that we can have this type of device over here. This is a channel. This is the channel of this thing which you can see over here. Okay. And this is how it has been fabricated. So you see here, for UV lithography, it's a vertical arrangement. It's a vertical optics. So you can see all these are optical elements, and from here the light comes, it falls onto this, and then the wafer is processed over here. So you can see this man, and then this is done in fabrication lab. This is called fab lab. Now, one thing you might have noticed, that there is always a yellow light over here. Why it is so? If you look at all fab over here, yellow light. If you see over here, again you will see here yellow light. Why this type of yellow light is there? Because it should not affect the yellow light, don't affect the silicon. Why? Because it is overlapping with the photonic band gap of the silicon, 1 electron. Okay, so that's why people use yellow light, so that the photoconducting property of silicon will not be affected during the processing. Okay? So this is what is a scene of a fab lab. Now let us go into the a bit of basics of it. So if you look at the semiconductor element, all these elements, हे सर्व जे आहेत याला म्हणतात periodic table, आवर्त सारणी. याला काय म्हणतात आवर्त सारणी म्हणतात. आणि हे केमिस्ट्रीमध्ये खूप फेमस आहे. केमिस्ट्री काय फिजिक्स मध्ये दादा आहे हा केमिस्ट्री पिरियडिक टेबल. जी आवर्त सारणी हे जे पिरियडिक टेबल आहे त्याच्यामध्ये हे सगळे येल्लो केलेले आहेत ना, झिंक, कॅडमियम, मर्क्युरी, टँटॅलम, लेड, स्टॅनस, antimony, tellurium, selenium, sulfur, phosphorus, silicon, aluminum, all these things, all these elements, they show semiconducting properties in one or the other way, in their compounds or alloys in some form, they show semiconducting properties. What is this semiconductor? Semiconductor, engineering wise, if you ask, it's a substance which has a conductivity in the range of in between the range of insulators and metals. Metals has extremely high conductivity. Insulators have no conductivity. So if you see the graph of conductivity, okay, with this material, these are fused silica is a excellent ceramic. It's an insulator. Diamond is excellent crystal, insulating crystal. Glass is insulator. Okay. So you see the range of conductivity per ohm per centimeter, 10 to minus 20, 10 to minus 16. So, but if you look at semiconductor, they have conductivity like 10 to minus 4, 10 to 0, 1. And if you look at metal, even for metal, if you see 10 to 4, 10 to 8, iron, copper, platinum. Okay? So, if you look at the range of the conductivity, engineering wise, if you are a semiconductor engineer, electronic engineer, you say that this is a substance which is in between insulator and metal, which having a conductivity value in between greater than insulator conductivity but less than metal. And then if you have this type of thing, okay, who discovered it? Who has seen it? Was a Michael Faraday who discovered this substance. In fact, what he discovered was he not only discovered this thing, he discovered that the electrical resistance of silicon, it reduces with temperature. It reduces with temperature, and same thing we have seen for germanium also. So that was the first evidence temperature sensor people have thought about to have. Okay, to have a for a narrow range, of course, let us say 0 degree to 100 degrees Celsius, which is having a change in the resistance. Okay, but then the first device was realized by this Professor Brown. Okay, and he made the first semiconductor device. How this semiconductor works? I mean, what if you look, most of you may have known the band structure. Okay, of you may know what is meant by band structure. Band structure consists of two bands, valence band and conduction. The valence band means the electrons which are in the valence band, and then they will start conducting. Okay, and they go into conduction band. But then this valence band and conduction band, they are apart in case of insulators, so that this forbidden gap will not allow any valence electron, because there will be no valence electron available, or there will be very few valence electron available in case of insulators. So there is a huge forbidden gap. They cannot jump from here to here to have a conduction of that. Whereas in case of metal, there is a total overlap. That's why you can have a free conduction. Okay, conduction free of course. So they are called as a conductor, electrically conducting material. And then what is in between? In between there is a Fermi level. In between, so on x-axis we have a Fermi level. On y-axis we have a electron energy. And then in case of metal, there is a overlap between them. Overlap. Whereas in case of insulator, there is no overlap. There is a huge forbidden gap. This band is called band gap. It's called band gap, electrical band gap of the material. And then in between metals, and you can see here there is a material which is having a moderate band gap, having a moderate band gap. So where you can have this thing. Okay, Fermi level. And now we are going to see how this is useful, how we can exploit this moderate band gap for our use. Now जर का तुम्ही सिलिकॉन बघितलं, इफ यू अगर सिलिकॉन का कॉन्फिगरेशन देखोगे तो सिलिकॉन इज 40. Silicon is 40. So if you look at the silicon configuration, so it consists of four. It consists of 2, 8, and 4. Four valence electron. It consists of 4 valence electron, and then these valence electron forms a covalent bond. So if you take pure silicon, it is insulator. If you take pure silicon, it is a kind of insulator. Then what to do? You insert impurity. So there are two types of impurities people put. One is p-type doping, other is n-type. We will talk about p-type first. So what to do? You dope your crystal, silicon crystal, by boron. Why boron? Because boron 5, it is 2, 3. So you will have a vacancy over here. So boron is called as the acceptor impurity. What boron called is acceptor. Why it is called acceptor? Because it creates a hole. As a charge carrier, and then that's why it is called as a p-type of dopant. Similarly is the case of the gallium also. And then the absence of electron creates the effect of a positive charge, and that's why it is called as p-type of dopant. Similarly, if you use phosphorus or arsenic, then phosphorus, arsenic, what they do, they create an extra electron. If you look at phosphorus, it is like 5. So it is 2, 8, and 5. So you implant silicon with phosphorus, there will be one excess electron from phosphorus. So they will create a this doping will create a excess electron, and then it will take a very few small amount of quantity impurity to create enough free electrons in the intrinsic semiconductor, or in the intrinsic silicon. Now, interestingly, if you look at it here, this is a band diagram of this thing. This n-type impurity creates the doping level near the conduction band, below the conduction band, okay, or it is, let us say, near the conduction. But if you look at n-type, p-type, it creates the hole or conduction level near the valence. It is on the top of the valence band. So as a result, there is a shift in the Fermi level. What is the Fermi level? Highest occupied electronic level at that temperature. Okay, it's called as a Fermi level. So you will have this type of thing. Now, if we have these two type of conduction, what will happen if I fuse it? So you can fuse it by two ways, and you can conduct it by two ways. One is called as a forward bias, another is called as a reverse bias. So in forward bias, you have P to P connection. Yeah, in reverse bias, you have P to N connection. So this is how the conduction process. So it will act as a kind of on and off. It will act as a kind of on and off kind of thing. So you see this how it will have a behavior in forward bias, okay, and then in the reverse bias. Okay, so that is how the PN junction will work. This is how a transistor. Now, what will happen if we fuse two PN junction? So you can fuse it by two ways. Either you have a NP and overlap P of second, or you can have NPN. So you have P and N and overlap N with each other. So you will have NPN transistor, you have, and otherwise you have PNP connector. So this is called collector base emitter and collector base emitter based collector kind of thing. So this type of configuration will have. So one is having a emitter kind of thing, other is having a collector kind of thing. So transistor is the first semiconductor device which you can realize, which act as a switching for the electronic signal. Then there are many other types of devices, like for example rectifier. Okay, this is also one of the popular devices where you can have a AC ripples you can rectify by this rectifier, and then there are many more. This is like an entire family of silicon semiconductor devices. It is having a diode, triode, then some thyristors, okay, and then MOSFET and MOS and things like that, more complex. So this is all how the entire electronic we are going to fabricate this. So first development of IC was done in long back in 1959, which was done by Kilby from the Texas. This was the first IC which was developed. Okay, and then how many chips were there? I think very few, 100 or 1,000 or 2,000 transistors were there on that IC. But now, if you look at the modern thing, this is how it looks like. Very small kind of, you know, transistor which has been developed in this silicon, and not only transistor, by other electronic components also you can have, which can act as bit and byte information to process. And as I told you, 4004 4-bit processor was developed in 1970. This was the first microprocessor which was invented by Intel at that time in 1970s. And then it was followed by 8080 8-bit processor. Okay. So this is what the thing which happened. So 1970 and other is 1975. This was the first ever computer which was developed in 1981. So it was like IBM PC. Okay. And it was very costly affair during that time to purchase this type of thing, because it was costing like anything. Okay, more than $5,000 or so. Okay, so let me say, so $2,000, $3,000. Okay, which include how many? 64 kilobytes of RAM. Okay, and if you see single-sided write-up of floppy disks of 5-inch floppy of 160 kilobyte of thing. Okay, so this was the IBM PC which was developed. And what was the processing frequency? It was 4.77 megahertz. And how much is your mobile worth? You see how much is the frequency of mobile data processing? It is more than it is now more than 2.65 gigahertz. Now the recent one is 3.12 gigahertz of processing. Okay, so if you look at the modern modern IC, it is a fully robust system which consists of a ALU, then instructive decoder, instruction register. So there is a registration, decoding and coding which has been done by ALU, arithmetic and logic unit. And then this is a three-state process in all the way: input, output. Okay, so and then it is connected to various types of. So there are many buses. I have typically showed you two types of address bus and data bus. Okay, 3-state. It's total 6-state of address bus. So there are many. One of the popular is like general purpose bus. Okay, or there are many other things. I have now forgotten everyone's name. Okay, not all is known. So this is what is a modern chip will look like. And if you go ahead, even for all your if you look at very modern thing, now they are coming on tunneling magnetoresistance kind of thing. Okay, which are even compact and flexible and this thing. So this is how it looks like, 10^10. So if with 5G technology, the number of transistors will be of the order of 10^10, 10^12. Okay, in a integrated circuit. So this is how it will look like, and everyone is in the race. Pentium and Latinium and AMD, and there are many guys who are in. So transistors are becoming smaller, high switching speed, and then reducing cost. All these things. So this is how the current IC will look like, with so many number of transistors of the order of 10^10 or so. So this is how I thought that I should share it with you. Then there are there are some reports on the smallest transistor. You see, they are really having a nano thing, 14 nanometer of the trench size. Okay, so really small transistor, nanotechnology really in there. Okay, so there is no, it is needless to say that there is no nanotechnology. It is in there. And people are also talking about a stretchable and foldable silicon integrated circuit. They are people are looking for the like fault tolerant integrated. So they are stretchable, foldable. Okay, so you can fold it, stretches. If even if it is impacted, it can be healed up. That type of thing. So this is a far-fetched thing. What is there beyond silicon? Is there anything beyond silicon? Can we do something beyond? So yes, we can go beyond silicon. Why? Because if you look at electron mobility of silicon, it is just 1000 centimeters per volt second. But if you look at germanium or gallium arsenide, it is more high. Even it is 4000, 10,000 centimeters. So they are faster. Their mobility is high. Same as for the whole. So people can think about the alternative of silicon. Instead of using silicon, we can go for germanium or gallium arsenide based kind of thing. So people are looking for such type of NMOS made up of germanium nanoelectrode. Okay, and then this will be the future of this thing. Okay, so with this thing I thank you all. आणि तुम्हाला सर्वांचे मी आभार मानतो की तुम्ही हे सगळं शांतपणे ऐकलं. आणि आय होप इफ यू हॅव एनी क्वेश्चन वी कॅन हॅव अ क्विक डिस्कशन. कोणाला काही प्रश्न असतील तर
ऑडियन्सला जर काही क्वेश्चन असेल तर त्यांनी चॅट बॉक्स टाका किंवा मी क्वेश्चन विचारले तरी चालू शकतात.
अगदी बिंदास विचारा, मराठीतनं विचारलं तरी चालेल, काही प्रॉब्लेम नाही.
तर आता नवीन नवीन जे प्रोसेसर आहेत, जे नॅनो टेक्नॉलॉजी जे आता 4 आणि 5 नॅनोमीटर वर गेले, आता बियॉन्ड 1 एका जेव्हा आपण 1 नॅनोमीटर वर जाऊ त्याच्यानंतर पुढे काय टेक्नॉलॉजी असेल नेमकी एक्झॅक्टली काय करावं?
पुढची जी टेक्नॉलॉजी, खूप छान प्रश्न विचारला. काय नाव तुझं बाळ?
अभिजित.
अभिजित, कुठनं आहेस तू?
मी नाशिक.
नाशिक मधनं. नाशिकला कुठे आहे? नाशिक माझं जन्मगाव आहे, त्र्यंबकेश्वर.
नाशिक मध्ये मी नाही सर, मी वणीच आहे, कसबे वणी.
अच्छा,
चंदगड.
काय करतोस तू? MSc करतोयस का?
हो, MSc फर्स्ट इयर.
व्हेरी गुड. आणि कुठल्या कॉलेज मधनं करतोय?
येस, दिंडोरी.
व्हेरी गुड, व्हेरी गुड. दिंडोरी, व्हेरी गुड. खूप छान प्रश्न विचारला की समजा आपण नॅनोमीटरच्या खाली गेलो तर मग आता काय आपण फेम्टोमीटर मध्ये करायचं, तसं नाहीये. तर याच्यामध्ये कसं माहिती काय, हे द मेन थिंग याच्यामध्ये जी गोष्ट आहे, याच्यामध्ये आपण अजून इलेक्ट्रॉनिक करंट नेतोय. आता विचार कर, याच्याऐवजी आपण समजा फोटॉनिक करंट नेला, म्हणजे तुझी इलेक्ट्रॉनिकची कन्सेप्टच बदलायची. इलेक्ट्रॉनिकची कन्सेप्ट असतो, सो यू नीड नॉट हॅव टू हॅव, तुला व्होल्टेज किंवा हे प्रोसेसिंग कशामुळे मिळतं, हे सगळं प्रोसेसिंग तुला इलेक्ट्रॉनिक्समुळे मिळतं. हे चेंज करायचं आता. आणि याच्याऐवजी काय करायचं, इलेक्ट्रॉन्स न वापरता फोटॉन्स वापरायचे. लक्षात. मग देन यू नीड नॉट हॅव टू बॉदर अबाउट 20 मिलीमीटर नॅनोमीटर आहे का, 1 नॅनोमीटर आहे का, 1 नॅनोमीटर आहे. यू नीड नॉट हॅव टू बॉदर. So people are switching about from electronics to photonics. Where everything will be done, all this thing, memory and processing of this thing will be done through the photon. Photon म्हणजे लाईटचा क्वांटा. तुला माहिती आहे ना फोटॉन काय?
हो, आता सर त्या कॅमेरामध्ये पण ते मिररलेस टेक्नॉलॉजी ती डेव्हलप झालेली आहे ना. डायरेक्ट इमेज कॅप्चर करून डायरेक्ट इलेक्ट्रॉनिक फॉर्म मधून डायरेक्ट हे करायचे, लाईट कॅप्चर करून ते काहीतरी.
पण त्याच्यामध्ये अजून इलेक्ट्रॉनिक डिव्हाइसेस वापरतात NMOS. पण हे जे क्वांटम कम्प्युटर्स आहेत, हे क्वांटम कम्प्युटर सगळे फोटोनिक बेस्ड असणार आहे. ओके, छान प्रश्न विचारला अभिजित, बढिया.
हो, थँक्यू.
अजून कोणी आहे?
हॅलो सर.
हॅलो.
मला एक प्रश्न आहे सर, की नॅनो कार इन आवर बॉडी, सपोज people infected with some cancer cell, the heart attack. So in future there is one option, nano car they are using to detect. How that? ते आपण
बॉडी मध्ये
करू शकतो. बॉडी मध्ये समजा अटॅक आला किंवा एखादी.
हो, करेक्ट. काय काय नाव तुझं बाळा?
अमोल सर्व्हिस.
अच्छा अमोल. ओके. तू कुठल्या गावचा आहेस?
सिन्नर.
हा सिन्नरचा.
सिन्नर
व्हेरी गुड.
सिन्नर.
अच्छा सिन्नरचा. व्हेरी गुड. तर अमोल ते कसं आहे माहितीये का की हे आज जे मी तुला सांगितलं हे प्युअरली ह्याच्यावरती होतं, इलेक्ट्रॉनिक्स ह्याच्यावरती. देर आर एफर्ट्स, देर आर पीपल हु आर वर्किंग ऑन द मेडिकल आस्पेक्ट ऑफ इट. म्हणजे त्याच्यावरती मेडिकल मध्ये काम करणारे लोक पण आहेत लक्षात, की जे जे इंटरेस्टेड आहेत, की जे ज्याचे नॅनो मटेरियल और नॅनो दॅट इज कॉल्ड एज अ मोटर. इट इज कॉल्ड मॉलिक्युलर मोटर. ओके. त्याच्यावरती पण काम करणारे लोक आहेत की विच विल बी यूज फॉर ऍप्लिकेशन फॉर लाईक हार्ट अटॅक आला तर तो ते ऍड्रेस करण्याकरता. येस तशा पण बोल. छान प्रश्न होता तुझा. व्हेरी गुड. अजून कोणी?
सर
हम्म.
या टॉपिक वरती नाही क्वेश्चन एक मला एक वेगळा विचारायचं आहे. आता जे नवीन आता इलेक्ट्रिक कार्स वगैरे जे आलेले लिथियमला अल्टरनेटिव्ह काही असू शकतो का लिथियम बॅटरीज?
लिथियम बॅटरीजला अल्टरनेटिव्ह म्हणजे सध्या तरी कसं आहे माहितीये का की यू कॅन म्हणजे तुम्हाला डिपेंड आहे की कशी तुमची रिक्वायरमेंट आहे. आता सध्या तरी लिथियम ऍक्च्युली बॅटरी जे आहेत कारमध्ये लिथियम बॅटरीज नाही वापरणार आहेत. कारमध्ये ज्या बॅटरी वापरणार ते निकेल बॅटरीजच वापरणार जे आपण आता वापरतो तो. फक्त एवढंच आहे की जे ट्रान्समिशन आहे त्याचं की जे आता फ्युएल वरती चाललंय ते ट्रान्समिशन विल चेंज. ते ट्रान्समिशन जे आहे ते पण बॅटरीवरतीच येईल. आणि ते जे बॅटरीवरचं ट्रान्समिशन येईल की ज्याच्यामध्ये तुम्हाला 2 आता बॅटऱ्या असतील आणि त्याच्यात ते बॅटरीला चार्ज करण्याकरता तुम्हाला सुपर कॅपॅसिटर लागेल. आणि तुमचे जेवढे इलेक्ट्रॉनिक डिव्हाइसेस आहेत त्याला तर लिथियम आयन बॅटरी आहेच, पण तुला निकेल हायड्रेट जी बॅटरी आहे जी कारला लागते, ओके, तर ती तुम्हाला आता 2 बॅटरीला म्हणून तर त्याला पण त्याला बॅकअप लागेल. पण मेन कसं आहे माहिती आहे का बॅटरी आणि कॅपॅसिटर मध्ये वर्किंग असं की त्याच्यामध्ये जो एनर्जी डेन्सिटी आणि पॉवर डेन्सिटीचा फरक आहे. ओके. त्यामध्ये कसं आहे की हे तुम्हाला लॉंग टाइम पॉवर देते बॅटरी, पण कॅपॅसिटर कसं तुम्हाला शॉर्ट ड्युरेशन मध्ये पॉवर देतो, सर्ज देतो पॉवरची. लक्षात म्हणजे तो फटाकन चार्ज करेल बॅटरीला. सो यू नीड टू वन मोर बॅटरी अँड बॅटरी सुपर कॅपॅसिटर बँक टू चार्ज इट. तर हे असं असणार म्हणजे इट इज अ येस ऑफकोर्स इट इज रिक्वायर्ड. आय मीन कारण की तुम्हाला शेवटी नको आहे ना पेट्रोल आणि हे कार्बन इमिशन जर का नको असेल तर डेफिनेटली यू हॅव टू गो फॉर दिस. जर का तू बघशील आता आपल्या भारतामध्ये 8% प्रमाण वाढलंय इलेक्ट्रिक व्हेकल घेण्याचं म्हणजे भारतासारख्या कंट्रीमध्ये. ओके.
आणि सर ते छोटे जर आपण एक छोट्या कॉम्पॅक्ट सेल मध्ये बनवून एक पॅकेट बनवलं बॅटरीचं तर ते त्याची ड्युरेबिलिटी जास्त राहील म्हणजे त्याची कॅपॅसिटी आय थिंक जास्त राहील माझ्या मते. छोटे छोट्या फॉर्म मध्ये सेल्स वगैरे केले तर आणि ते एकमेकाला अटॅच करून.
डेफिनेटली डेफिनेटली डेफिनेटली. अजून आहे का क्वेश्चन कोणाचा आहे?
I think no question more, sir.
ओके या अमोल.
Yes, sir. We move toward final session.
I'm Miss Stanley Shankar, project staff on MIT sponsored project entitled as creation of R&D culture in electronic materials among SC and women students in Maharashtra at Semiconductor. On behalf of project team, I would like to express my sincere thanks to all the faculty members and students for joining in the webinar. Also, I would like to express my deep sense of gratitude and thanks to today's guest speaker for this section, Dr. Alegaonkar. Sir, it is very interesting and informative talk. Thanks again.
थँक्यू सो मच मॅडम. आणि अमोल तुला पण थँक्यू. सर्व सिमेंटच्या म्हणजे मित्रांना, रिसर्च करणाऱ्या सर्व दोस्तांना माझ्यातर्फे थँक्यू सो मच. वी विल मीट अगेन.
Yes, sir. Yes, sir.
Thank you so much.
Now session is over. Okay, sir. Thank you.
Yeah.